In order to solve efficiently the problem, the proposed methodology is outlined in the slide. First, the main idea is to define initialization methods that could help to accelerate the convergence and could be useful to reach quickly the optimal solution. Then, plug the initial solution into the column generation approach and then to use different methods to identify profitable columns that could help to reduce the objective functions and find an optimal solution. Three main methods were identified as useful to generate the subsets and also to accelerate the convergence of the overall process. The first one, named intensification, adds several columns at each iteration based on the reduced cost criteria. Other one, known as diversification, adds several columns to the master problem at each iteration of the column generation algorithm, but not based only on the reduced cost criteria, but also in the structure of the column. A third set of instances was solved using several optimization engines. The design of the instance was based on the ones proposed by Sevan and Rossi, using different sizes and sensors and targets randomly deployed in a sensing area. In addition, the sensing range of the sensor was varied in order to evaluate how it affects the problem difficulty. The first fact that was evidenced is that it is possible to find a point in which the column generation algorithm takes more iterations and this behavior was evidenced in all the instances size that was tried. When observed the evolution of the objective function, it is evident the appraisal of a tail-off effect. It is while a near optimal solution is approached considerably fast, only little progress per iteration is made when overall process is close to an optimal solution. Regarding to the associated bar problem, it is possible to observe how appears an oscillatory behavior. It is well reported for several authors that this is a clear signal of instability problems, and previous experiments have led to conclude that this is a cause of convergence problem. All the evaluated instances have shown the same problem, so it is possible to conclude that it could be necessary the use of some techniques to avoid that this behavior appears. And maybe we can accelerate the overall convergence, and the column generation algorithm could be accelerated. To summarize, it is possible to observe that the most of solution shows degeneracy signals caused by the fact that it is possible to obtain different alternative solutions at each iteration for the auxiliary problem. Also, it is observed that some iteration of the algorithm doesn't have any effect in the objective function value. All these factors combined led to a slow convergence to the optimal solution. As is possible to observe in this graphic, by some instances the problem is even worse. As a result, I have been working mainly on the set of instances that actually shows the greatest problems. So it will be possible to extend the results to the other set of instances. Since now I am going to present a set of different methods that I have been using to try to overcome the convergence issues in the column generation algorithm. Okay. In order to avoid instability and accelerate the convergence of the column generation algorithm, it is possible to present a taxonomic model of methods that have been used for several authors and have shown good results. There exist three main methods to reduce the large oscillations observed in the dwarf problem associated with an optimization problem solved using the column generation algorithm. Qt-plane method works on the dual space-generating efficiently planes equivalent to generate columns in the original problem. The way in which the Qt planes are generated helps to reduce the number of iterations and, in general, could reduce the total number of iterations of the column generation algorithm. Integral point stabilization is an acceleration method for column generation algorithms. It addresses degeneracy problems and convergence difficulties by preventing dual variables from taking extreme values. To do this, at each iteration it selects a dual solution inside the optimal dual space instead of an extreme dual point. Also, it is common to observe that several authors propose to return several columns at each iteration of the column generation algorithm. This strategy, known as intensification, uses the reduced cost criteria to select what column must enter to the problem at each iteration and return several columns, avoiding unnecessary iteration. As a disadvantage, such a strategy could have an larger effect on the size of the total problem. But most of the columns are useless because just a little portion of this could be in the optimal basis. On the other hand, some authors recommend not only to add good reduced cost columns, but also include diversification features in the column generation approach. To do this, it is recommended to select the columns that must enter to the basis based not only in the reduced cost criteria, but also including columns that have a different structure to the optimal one. This strategy was named diversification and have shown good results, at least in some experiments present for some authors. In order to overcome the column generation issues and to prevent the dual variable from taking extreme values, the most recognized strategy proposed in the literature is to try to limit the distance traveled by the dual variables at each iteration. The general strategy proposed consists in perturbing the problem by including some slack and surplus variables that, from the viewpoint of the dual problem, are avoiding to move far away from the actual dual solution, and this leads to avoid the large oscillations that I previously presented in a previous slide. Okay. The first method that we are going to evaluate, that I am going to present right now, is the one proposed by Marsden. Okay. This was maybe the first stabilization technique proposed to avoid degeneracy problems. In this method, a modification is introduced in the master problem by adding a new set of primal variables to a row actually, that in the dual problem define boxes around the previous value of the dual variables. Okay, this strategy works interactively, bounding the dual values, and to doing this, we can avoid the large oscillation that I presented in the previous slides. Okay. In this method, we could say that we have defined a three piecewise. No. In this method, we define a one piecewise linear penalization